Okay, we're going to look at a problem dealing with Gauss's law. This is prototype number 8. Let's consider a long non-conducting cylinder with a radius equal to 12 centimeters with uniform volume charge density of 5.0 nanocoulombs per meter cubed. Our quest is to find the electric field 5 centimeters from the axis of the cylinder. That means we're inside the cylinder. I show the actual cylinder containing the charge distribution in red and the 12 centimeter radius. Our imaginary surface through which we will calculate the electric field, our Gaussian surface, is shown in blue and is 5 centimeters. Now you should be able in your mind to state Gauss's law. What is it? Well, it's simply that the electric flux through a closed surface is equal to the enclosed charge divided by epsilon naught. Now, state the above in equation form. Pause the video, write down the equation for it, and then restart the video. And that's simply the electric flux equal to the closed integral of E dot dA equal Q enclosed over epsilon naught. Now the question is, can I calculate the charge enclosed by the 5 centimeter cylinder? How do I do that? Remember that I'm given the volume charge density 5.0 nanocoulombs per meter cubed. How do I get to the total charge given the volume charge density? Go ahead and try your hand at it, pause the video, and then restart it once you think you've got it. Let's start with the idea that we have a length L of this cylinder. And assume that that is the volume that encloses the charge. Well, it is the volume that encloses the charge. Now go ahead and calculate the charge enclosing that volume, write it down, and then restart the video once you have what you think is the charge enclosed. And here I have it as the volume is equal to pi r squared L. And we can say that the volume is pi times 0.005 meter squared L in total meter cubed. So once again, we need to have that to calculate the enclosed charge. And so the total enclosed charge is the 5 nanocoulomb per meter cubed times the volume, which is pi times 0.005 squared L meter cubed. And we wind up with 3.927 times L nanocoulombs. Now in the integral, we've got the right-hand side. Now we want to get the left-hand side. So in the integral, what does dA refer to? Pause the video and think about it and answer the question. It's of course the surface of the cylinder. We're referring to a small piece on the surface of the cylinder. Is E parallel to dA everywhere on the surface, and is it constant? Once again, pause the video, think about it, draw dA on the surface, an arbitrary dA, and then the way in which you think the electric field is going. Yes, it is. So now we can write the E times the integral of dA, where I have gotten rid of the vector sign since E and dA are parallel, is equal to 3.927 L nanocoulombs over epsilon naught. What is the integral of dA? Pause the video, think about what that question asked, and if you have the answer to that question, then restart the video. It is 2 pi times 0.005 L. It is the surface area of the small cylinder that encloses the charge. Remember, it has got to be a surface that encloses the charge under consideration. It has to have a certain symmetry about it, and it has to be a surface where the electric field is constant or zero. For E times 0.031 L meter squared equals 3.927 L nanocoulombs over epsilon naught, and which, canceling out the L, I have that E is 125 nanocoulombs over epsilon naught. And a couple points about this problem. One is, you notice I didn't really do anything with the ends. You should be able to figure out why I did not do anything with the ends. Take some time, try to figure that out. End of prototype.